All right. I am going to try to make up in long-term vision what I lack in enthusiasm with respect to my colleague, Dr. Summers. He's a tough act to follow. But I want to spend about 45 minutes here telling you about, in some ways, the last 300 years of astronomy and the next 30. Where we've been and where are we going in terms of the biggest questions we can possibly ask. Well, astronomy asks big questions, naturally. We're thinking about big things, right? Asking big questions. I'm going to talk about two in particular. Where did we come from? And are we alone? Now, this is more general, bigger than just how do galaxies form or how do planets form. These are really, these are civilizational scale questions. These go back forever, right? And they'll probably go far into the future. These are questions that have been asked as long as people have been doing astronomy. Of course, naked eye astronomy started as soon as the first caveman looked up into the sky, but telescopic astronomy, using actual telescopes and lenses, began with Galileo Galilei, officially in 1609. Here he is demonstrating his little telescope for the Doge of Venice in that year. And one of the things that Galileo is famous for discovering, among his many epic-making discoveries, was the satellites of the planet Jupiter. So there's Jupiter, and there's the 4 Galilean satellites, we call them, along with the well-dressed Italian. And this was really the piece of evidence that convinced people in Europe in the Renaissance and then eventually worldwide that there was a whole world out there beyond the Earth. It was not merely terrestrial. It wasn't just human. There was this otherworldly universe out there that we could actually learn something about. I told you this was going to be a fast history. We're going to skip ahead by more than 100 years now. I chose to illustrate the next advance with a brother and sister team named the Herschels, William and Caroline Herschel. By the time of the Herschels, they were building reflecting telescopes, actually invented by Newton, but William Herschel had a 40-inch aperture with this big rotating apparatus that pointed it around at the sky. The Herschels are famous for having discovered the planet Neptune, not known to the ancients. This is William Herschel's drawing of what he thought the Milky Way galaxy must look like, from looking at the band of stars on the sky and trying to figure out how that would look if we weren't living inside it. It's not that bad, but I think you can compare Herschel's image of a disk galaxy with Hubble's image of a disk galaxy in the lobby and see that he was doing pretty well for his time, but we can do much better. There's a whole other technique of astronomical observation which becomes absolutely critical a little bit later, so I want to introduce it rather early. That's called spectroscopy. You can maybe imagine what this is. There's Newton with his prism, right? Everybody's played with a prism when they were a kid or something, You hold a prism up to sunlight, what do you get? You get a rainbow, right? Roy G. Biv, red, orange, yellow, so on and so on. That is the fundamental technique that we still use today. I use it in my daily life as an astronomer to figure out what stuff is made of. And the reason is, if you take a spectrum like this is essentially the same kind of measurement as Newton's prism. But if you take a spectrum like this or like this is one of the first that existed by the Germans Fraunhofer and Kirchhoff in the 1800s, you could look for these lines. See these lines? This is a solar spectrum. And if you see these lines, that's absorption. That's an atom of a particular kind in that environment absorbing light. So the light doesn't get to you. This is the light that comes out of the sun. The ultraviolet, the blue, the green, the yellow, the orange, and the red. But where it's absorbed, the spectrum goes black. And that's, for instance, how we know that the sun is made of hydrogen and helium and has some iron and carbon and nitrogen and oxygen and all that interesting stuff. Spectroscopy is the way that we do the physics side of astrophysics. We figure out what stuff's made of, what its dynamics are, from taking these spectra. That's Newton's telescope, by the way. Okay, forward into the 1920s. This is Edwin Hubble himself. And he used this telescope here at Mount Wilson, which is 100-inch, to do what he's famous for, which Frank just mentioned, which is to measure the expansion rate of the universe. Now, he did that by observing exactly the stars, some of the stars that Frank mentioned, the Hubble variable stars. If he knew how fast they brightened and dimmed, he could work out the distance. using spectroscopy, he could work out their velocity by measuring what's called the redshift. As an object recedes from us, it gets redder. As it moves towards us, it gets bluer. Hubble was able to take redshift and distance and work out that the entire universe was expanding. That's why he's as famous as he is. That's why we named our first space telescope after him. Here we are. This is Hubble. This is the outdated version of what you just saw. I didn't want to steal any thunder. But here's Hubble doing its thing. This is the ultra deep field taken with Hubble's advanced camera for surveys. There's thousands of galaxies in there. I think this one right here, that's the only object in the field that's a star. Everything else is a galaxy. This is to date the deepest picture of the universe that Hubble, and therefore anybody, has ever taken. So that brings us up to almost the present time. We figured out first of all, thanks to Galileo, that there was a universe out there to learn about that wasn't terrestrial. We figured out that we could discover objects beyond what the naked eye or even small telescopes could see. We could see the outer planets. We could see parts of our own galaxy that we live in. Hubble showed us that the universe has a cosmology, that it has a dynamic all of its own, that it's expanding, that there's a history to the universe, that it had a beginning point. It hasn't always been here. All of those things flow from Hubble's discovery of the expansion of the universe. And probably the most epic-making or significant from the historical point of view discovery in our lifetimes has been the discovery that there are planets orbiting other stars in our own galaxy. This came around 1995 with the first discovery of what's called an exoplanet, a planet around another star, by a Swiss group of astronomers using a telescope in Switzerland. And what's really important about this is that they used this same technique that I introduced, spectroscopy, right? So let's go through this in a little bit of detail just to show you how it works. Here we have a star and a planet, a star and a planet. And the star and the planet orbit their common center of gravity. That's one of Newton's laws of gravitation, is that any two objects orbiting will orbit their common center of gravity. That means the star, even though you think ordinarily the planet's orbiting the star's fixed and the planet moves, but it's not quite that way. The star has a reflex motion. It moves a little bit in response to the gravitational force of the planet. So the star wobbles back and forth just a little bit, right? And that's illustrated here in the fact that there are two pictures of these stars. When the star's moving toward the Earth just a little bit, the light gets slightly blue shifted. And when the star's moving away from the Earth just a little bit, it gets slightly red shifted. And so by watching the stars wobble back and forth, just like this, these astronomers were able to prove that there was a planet there. We still can't see that planet. We can't take a picture of that planet yet. That's what we're driving at. But you can prove that the planet's there by measuring the motion of the star that's gravitationally introduced by the planet. That was the greatest astronomical discovery of my lifetime, arguably. People would tell you that the acceleration of the expansion of the universe is equally important. There's a Nobel Prize for it out in the lobby, but I think this one's right up there. And this has kicked off a whole revolution in the way astronomers think about our field and the way I think the public thinks about our field, because this is addressing some of the deepest questions that we can address. Like I said, are we alone? Is there any other life out there? So where do we stand now? That was the last 300 years. I'm going to talk a little bit about the present in the next 5 to 10 years, and then I'm going to tell you what we see coming down 20 or 30 years from now. It happens that we're all fortunate to live in what really is a golden age of astronomy. And the reason for that is that funding agencies and the public have bestowed on astronomers an incredibly rich array of frontline instrumentation. The kinds of things that were far, far beyond the imagination of those early astronomers, even Hubble, who lived in the 20th century. There's the giant space telescope named after him. There's the Kepler Observatory, which looks for planets. I'll say more about that later. The Chandra X-ray Observatory. This is a UV satellite called ultraviolet imaging telescope called GALEX. There's the Spitzer Space Telescope, which is still going after about 11 years. That's an infrared space telescope. There's the European Herschel mission. There's a huge number of 8 to 10 meter telescopes on the ground, the Very Large Telescope, the Keck Observatory. We have lots of radio facilities like the Very Large Array. When you add all of these things together, you can see, you've probably seen, since you're all probably paying a bit of attention to this, you can see the discoveries of these things come together and mix and teach us new things on a daily basis. We really live in a real revolutionary period for astronomy, and we're fortunate to do that. I would like to be able to spend 10 or 15 minutes telling you about everything that Hubble has done that's awesome. It would take me a lot longer than 10 or 15 minutes to get through all of that. But what I think I will do instead of that is just point out the fact that Hubble is turning 25 years old this year. And that's amazing for any space satellite of any kind. The fact that we've managed to keep Hubble operating as an observatory for that long, and not only that, but make it better every 5 years, thanks to the human servicing, has made it by far the most productive astronomical observatory of all time, and arguably the most productive scientific facility of all time. Because it's turning 25, everybody here in the building is going crazy planning all kinds of events and talks and presentations, and we have a whole conference devoted to this. So instead of saying, here's Hubble's greatest hits over the last 25 years, I think you should just follow this website, and you'll see we have great video presentations coming out. We're going to have a big splash in April when the birthday actually rolls around. It's going to be fantastic. So I'd rather spend more time talking about the future than the present, so I'm going to move on to the immediate future for us, the Hubble 2.0, so to speak, which is what we call the James Webb Space Telescope. Now, if you look at Hubble, here it is, and then you look at JWST, they don't look anything like each other. Nothing, really. I mean, except that there's a mirror there, and there's some instruments in the back, and there's some electronics. They're very, very different beasts. The reason is, Hubble's not only 25 years old, but it's a giant steel tube with a big piece of glass in it, right? If you go out in the lobby on your way out, and if you can make it past the Andromeda image, back into the outer lobby, you can see there's these banners hanging from the walls, and there are pictures of the Hubble and the Webb primary mirrors to scale. So you'll see the Hubble primary mirror about 2.4 meters across, which is about like this, and the Webb mirror just dwarfs it. It goes all the way to the ceiling, and it's so big that we can't actually print it on a banner. It's just a piece of it. So I suggest you check that out on the way out. Hubble is designed to be a telescope that's optimized for observations in the infrared wavelengths. Those are wavelengths beyond what you can see with your eye. Light becomes blue, and then green, and then red, and once it's past red, you can't see it with your eye anymore. There's some insects that can, some probably nocturnal animals that can, but humans can't. The reason we're doing that is to pick up a bunch of stuff that we can only see at those wavelengths. I'll go through a bit of the science case. This is a zoom on Hubble's deepest image, that ultra-deep field that I showed you. And then at the end here, we're going to try to re-simulate that image as it would appear for JWST. So there it is transitioning to what JWST sees. You see it's a sharper image. That comes from having a larger telescope. But not only that, not only do our pictures of galaxies get sharper because we have a larger telescope, but we can suddenly do all kinds of science here that we couldn't do before. These galaxies, the red ones, the old ones, the really distant ones, become much sharper and much more easy to detect. Just let that one run again, because it's kind of cool. JWST, in the same time, will be able to go almost a factor of 10 deeper, so take images that are detecting objects about 1/10 as bright as what Hubble can do in the same time. It's going to be pretty amazing. My personal favorite science case, this is something I actually plan to do with JWST once they hand over the keys, is to look at very dense stellar fields. This is one of those globular clusters that Frank pointed out in the image of Andromeda. This is a globular cluster in our own galaxy called Omega Centauri. You see there's just, this is actually not a Hubble image, but close enough. This is a Hubble image in here, and you see it breaks up into individual stars, right? Blue star, red star, blue star, red star. JWST is going to have this amazing device on it called a micro-shutter array, which is this array of little electronic doors. And we can open and close those doors at will and take observations of individual stars. So we can open that door and take an observation of that star, open that door and take an observation of that star, and just leave the others closed. So we can pick out stars to observe in these fields. We can work out their age, we can work out their metal content, we can work out what this cluster came from and where it's going, all from taking spectroscopy of these very dense fields. This is the scale of those little electronic doors at the scale of a human hair. So pluck out a hair, hold it up and say, they made 250,000 of those little doors smaller than a human hair in the space of about 3 inches square. It's quite a device. By the way, it operates at 300 and something degrees below zero, too. JWST as an infrared optimized telescope is going to turn images that look like this one, very much like the pillars of creation that Frank just went through, into images that look like this one, right? In other words, peering through this obscuring dust to see the star-forming regions, the young stars right there, and the jets that they power. We're going to start seeing hundreds of images of star-forming regions that look just like this with JWST. So once we have done that, and I should just say, this is something that hasn't happened yet, right? JWST is supposed to launch in about 3.5 years at the end of 2018. We expect it to operate, we hope, for 10 years. So that'll carry us through almost the end of the next decade, 2028, 2030 perhaps. JWST, like any telescope that's come before it, it's intended to revolutionize things. It's intended to bring us knowledge that we never had before. And more than that, if it's anything like Hubble, it's going to teach us to ask questions that we never thought. In other words, the thing we build it to do is actually only a bit of what it does. Most of what Hubble's famous for are things that its designers never imagined. They're questions they never thought to ask. And that's because as science moves along, you come up with new discoveries, and every new discovery raises a new question. So it's very hard for us to predict where our field is going to be in 2028, at least when it comes to deep infrared observations of the universe. So where do we go from there, right? Once we've got JWST, and we definitely will get it, where do we go then? Well, I like to motivate our work with this really fantastic quote, not from an astronomer, it's a biologist. A rather famous biologist at Harvard, Ed Wilson, famous for ants, actually. He's written a lot of wonderful books about science generally and his life as a naturalist. And his claim very recently was that the most important experiment in biology is the search for extraterrestrial life. Think of this. This is a world-famous biologist telling us that the most important experiment in modern biology is an astronomy observation, right? That tells you something very important about where our field is going in the next decades. And it's not just Hubble, it's not just JWST. NASA has deployed and will deploy a whole array of missions at a smaller scale. These are not the giant, multi-billion-dollar flagships, but it has deployed the Kepler mission, and there are 2 coming down the pipe called TESS, and W first after that I'll speak about briefly in a moment, which are designed to address this problem that Wilson has posed. How can we find planets? How can we find planets that might be bearing life? And how can we find out if life is actually there? So we're on a pathway. Kepler's great discovery has been of Earth-sized planets. Kepler's been very good at finding all kinds of planets, but it's especially good at finding Earth-like planets. And it's done that with exactly the same it's done that with an observing technique that I'll describe in a moment, called transits. But the real important observation is that 1 out of every 5 sun-like stars has an Earth-like planet. 1 out of every 5 sun-like stars has an Earth-like planet. If you go back after the Andromeda image, you're going to see millions of sun-like stars. That suggests that there are probably millions to hundreds of thousands of stars with Earth-like planets in that image, right? Just statistically, right? And in our own galaxy, there are probably millions to tens of millions of stars with Earth-like planets. That is a discovery that even those astronomers who discovered the first exoplanets couldn't really imagine. This is a very new result. This is as of 2014. Well, we're not only looking for Earth-like planets if we want to solve Wilson's puzzle, we're looking for Earth-like planets in what we call the habitable zone, right? You might think of this as a bit of a Goldilocks problem. If a planet like the Earth, let's say, is at the position of Venus in our own solar system, or even worse, Mercury, it's not a comfortable place where you might want to go to the beach or play golf. It's like Mercury, where it's 700 degrees during the daytime and 700 degrees below, or 400 degrees below zero at night. It's not habitable. It's too hot. While if you're at the distance of Mars or beyond, also not good for going to the beach and golfing, it's too cold. So the habitable zone is more or less defined as where the radiation from the sun is just right so that water is in liquid form at the surface temperature. Because water is the key ingredient of life. It's 70% of all of our bodies. It's a bummer if the 70% of your body that's water freezes. So in order for a planet to be called habitable by the astronomical standard, it has to be in that region where it's not too close to get too hot and boil off all the water, not too far away to get too cold and freeze all the water. It has to be in this habitable zone, the HZ, habitable zone. So we have missions that can find Earth-like planets. Kepler has done it. We have a definition. We understand where those planets should be around their stars to be habitable. Once we've found them, how will we answer this question? Is there anybody living there? Is there life there on that planet? And it turns out this is a pretty straightforward problem when you think about it. It's a challenging observation, but it's a pretty straightforward problem. And that's because if you take a spectrum, just like Newton's spectrum of the sun with a prism, just like Fraunhofer's spectrum of the sun with his grating, there are features in the spectrum of the Earth that betray the presence of life on the Earth. We call them now biomarkers. It's a marker for a biosphere, a biomarker molecule. The easiest one to pick out, if you have the correct wavelength range covered, is the water vapor. These big divots in the spectrum here are from water. I think my next one is a little better. Nope, okay. These big divots in the spectrum here are from water. Light hits the Earth's atmosphere. Some of those photons from the sun get trapped by a water molecule and never go anywhere again. They get re-radiated into the infrared. So those photons, that light drops out of the spectrum, and it shows up just like that. There's also here the effect of the dust in the atmosphere, and then the ozone in the atmosphere, which is what protects us from the ultraviolet radiation. That introduces a very clear-cut drop in the spectrum. There's oxygen, the molecule we're all breathing to live, has these little signs right in there. Ozone is itself a very important biomarker because it doesn't exist with these other molecules in the absence of life. Ozone is a very clear signature that you have biochemistry going on. And then finally, these other things, carbon dioxide and methane, which are produced, carbon dioxide mainly by living people and then consumed by plants and then consumed, oxygen is consumed by us. Methane is another case where it's either emitted by bacteria or by animals. So if you can detect all of these biomarkers in the spectrum of an Earth-like planet in its habitable zone, you have the answer. That tells you that on that planet at least, there's strong evidence that there's life there, creating these signatures which otherwise would not exist. This is not what Mars looks like. This is not what Venus looks like. The uninhabited planets in our solar system don't look anything like this. The Earth does because we live here along with a lot of planets. So one way to detect a biomarker is to use the method that Kepler has used to detect planets, and that's the so-called transit method. This is an illustration of it. It's really cool, actually, to see. If you have a star and you have a planet orbiting that star, if it's oriented just right? If the orbit of the planet is more or less in the plane that you're looking in, that planet will pass in front of the star and it will make an image of the star just a little tiny bit brighter. Like it'll take 1 in 10,000 of the photons out of the image. So you'll have to, if you can measure 1 part in 10,000, you can detect this. And you can then measure the planet's atmosphere if the planet passes in front of the star by looking for these spectral features in the light that passes from the star through the planet's atmosphere and into our telescopes. So this is one way to detect these biomarker molecules, but it only works if the planet transits, right? It only works if this happens. If the star and the planet is oriented just so that the planet every once in a while passes in front of the star. If it's oriented a different way, where you say you have the star and the planet's going around it like this, it never actually passes in front of the star and it doesn't work. And that's actually the case most of the time. Because the orbits are just random, you have to be lucky for them to transit like this. So that's probably not going to be the way that we figure out, at least for lots of nearby planets, whether they have these biomarkers or not. Right? But anyway, this is a technique that we will use with JWST. Going back to that fantastic observatory. JWST may be able to use this transit technique to detect some biomarker molecules, especially water and methane, on what are called super-Earths or water worlds. So something that's 2 times or 3 or 4 times the Earth's mass, rocky in the core but surrounded by a big ocean. JWST might be able to detect water and methane on those planets. The spectrum would look like this, and I know this appears to be a total mess, but it's a simulated spectrum, by the way. This is not real data. One reason you know that is that the telescope is still in parts on the ground. And number 2, it looks a little better than real data actually would. But this is a simulated spectrum with JWST because, believe me, all the astronomers are ramped up. We're thinking about it. Even though it's in parts on the ground, we're launching it in 3 years, and we're ready to go, right? So we have to start thinking about what we're going to find. So JWST may be able to reach these water world planets, but it's not going to be able to get to genuine Earth-like planets, just like the Earth, one Earth mass in their habitable zones. And it's certainly not going to do that for a large number of planets. So it's a step in the right direction. It's a way to prove that the techniques work. It's maybe a way to make an important discovery. There's a water world out there with something to look at, but it's not really the answer to Wilson's claim. So what is the answer? What is going to get us this evidence that there's a separate evolutionary pathway for life, there's been a separate origin of life on another planet in our galaxy? The ultimate goal really is another living Earth, like our own. We already know, school children on Earth already learn that there are these worlds orbiting other stars. And what we'd like is for the future generations, and I don't mean the distant future. I don't mean 1,000 years from now. I mean my children, right? Possibly their children, but probably my own, right? Next generation school children. To know with the same certainty that we would know this, right, that there's life on some of those worlds. An increasingly large number of astronomers, myself included, that's why I'm here, but a large part of our community has come to the view that we can actually do this within 2 decades. Because we're starting to see it. We have the technology. We have the ability to build a telescope that can do this. So how will we do it? Well, it's much different from what I said Kepler does and what JWST will do. Because what we want to do is break open this restriction of having to have the planet pass in front of a star every once in a while. That doesn't happen very often for typical stars. Statistically, we've worked out that 20% of sun-like stars have planets, but that's by extrapolating from a much smaller number of measurements with Kepler. So the way to really prove this works is to just figure out a way to take a picture of the planet. Go out to the 1,000 nearest stars, find the planets there, and take a picture, right? That's worth 1,000 words. So what we're going to try to use is an instrument called a coronagraph. And I don't want to get all into all the technical and optical jargon that's involved here, but basically what you do is when you point your telescope, you put something in the way that blocks the starlight so you can see the planet. Now I have here an illustration using a star, a bunch of planets in the habitable zone around that star. It wouldn't have that many. They would all gravitationally eject each other. But that's just a model. And the idea is to have the coronagraph block the starlight, for a reason I'll explain in a minute, so that you can see the planet. Now, we already do measurements with things like coronagraphs. In fact, they were invented to study the sun. If you want to study anything near the sun, like the corona of the sun or a comet, that happens to be a comet right there, This is from a NASA solar mission. You have to block the sun out because the sun is the brightest thing in the sky, right? You wouldn't see anything near it if you didn't block it out. So people have figured out a way to block out starlight to see stuff nearby, and that's what we intend to do. The idea is to null out the stars so you can see the planets there, right? But it's really, 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 really hard, right? Because the planet is 10 billion times fainter than the star you're looking at. Now, the kinds of stars we're talking about are literally the kinds of stars you can see if you walk out into the street, San Martin here, and look up. They're that bright. They're bright stars. They're not the 28th magnitude stars that you're seeing in the Andromeda image in the lobby. These are bright stars. But the planet, because it doesn't emit any light of its own, it's only picking up the light that the star shines on it, right? It's picking up Earth shine, right? It's 10 billion times fainter than the host star. So how in the world are you going to take a spectrum of a thing that's sitting right next to something that's within a tenth of an arc second of something that's at 10 billion times brighter? This is a real engineering challenge. All right. In fact, this problem, detecting an Earth-like planet in its habitable zone, a tenth of an arc second away from a bright star that's 10 billion times brighter, is actually no harder than this problem. So if you figure out how to solve this problem, you can figure out the planet, right? It's this problem. Let's put a telescope in Baltimore, and let's put a searchlight in Los Angeles, and then let's put a firefly next to that searchlight. If you can solve the problem and find the firefly for all the searchlights in Los Angeles, from Baltimore, you got it fixed, right? It works. That's how challenging this problem is. I don't want to minimize the challenge involved here, and this is why it's going to take us 20 years to get to this point. But it's actually something that people who build instruments and work with telescopes on the ground in space are spending their careers trying to figure out. We have a whole group of people here in what's called high contrast imaging. Believe me, this is a high contrast, faint thing and a really bright thing. They're looking for the fireflies in the searchlights. So I think we can do this. What will it take? Well, ta-da! The mission I've been teasing all along is something that we've started to call the High Definition Space Telescope. It would be a new space telescope following on JWST. It would orbit at the Earth-Sun L2 points at the same place JWST is going. It's sort of a gravitationally happy spot a million miles beyond the moon. We'd like to see an aperture for the telescope of 10 to 12 meters, which is about the same size as the room here. So, not small. More like the room in this direction than that one, but still, it's big. It has to be a deployable mirror, just like JWST, so it'll all fold up origami style and fit in the rocket. Covers ultraviolet to near-infrared wavelengths. We'd really like for it to be more like Hubble and less like JWST, so that robots or astronauts could go in there and replace the instruments. That's been the reason that Hubble has been so successful over 25 years. That's the reason it's lived that long. So that's what we'd like. And of course, these things take time, so we're looking at 2 decades or so before we can launch. This is a comparative mirror sizes. There's the Hubble mirror. If you go out in the lobby, as I said, you can see that banner that tells you how big it really is. That's JWST to scale. And our high-definition space telescope is this 12-meter thing. It's pretty big. Okay, so why does it need to be so big? Let's take the stars within 200 light years, which is about 70 parsecs. That's all the stars from the list of actual stars at that distance. Okay, that's our galactic neighborhood, and the sun's in the center. Okay. Let's now say, well, we know that about 20% of those have Earth-like planets. We don't know which ones, but let's just randomly pick 20% of them. If you only build a 5-meter telescope, you only got a few, right? But if you go to 10 meters, now you're starting to talk about real numbers. And the reason that matters is that we don't have to be lucky. It's possible that of all the Earth-like planets, if every Sun-like star has an Earth-like planet, it might be that only 1% of those have just the right conditions to have developed life, to have these biomarkers, to have bacteria and bipeds, right? So we don't want to gamble too much, right? If you're going to build a big telescope and launch it into space and really, spend a lot of money and waste a lot of people's time, you don't want to gamble on just doing it with 10 planets, because let's say if only 1% of those planets have life and you only roll the dice 10 times, you're not going to win, right? So what we want to do is roll the dice enough times that we know we're going to come up, or we can really predict confidently we're going to come up winners, even if the dice are loaded against us. So it turns out the number you really need is more like 50 to 70. We'd really like 100 planets. And that forces us to these very large apertures because we have to use stars that are progressively further away and planets that are progressively fainter. So that forces us to be in this region between 10 and 12 meters to pick up 70, 50, 70, 100 planets. That's a 10 or 12 meter telescope. That's, as I said, that's critical because we don't know the actual rate of life on these Earth-like planets. And we have to improve our odds by aiming high. Okay, so it's a simple equation between a large telescope and 50-ish Earth-like planets. Maybe life, we don't know. We have to first find these by going to the star, nulling out the starlight, imaging the Earth-like planet, taking a spectrum, and hoping that we get this spectrum, right, with the water, the oxygen, the ozone, and the methane. That would be the grand prize. That would be the spectrum of the Earth-like planet and the habitable zone of its star, showing biomolecular molecules, and that's going to be, in the newspaper, right? I chose my birthday in 2035 as the day that the discovery is announced. I guarantee you will never see a spectrum like that. They'll show some artist's conception of the planet because they never show spectroscopy in the newspaper. Presumably Bob Dylan's not going to have a new record out that same day. It'd be like 98. But that's not all. You're not only discovering Earth-like planets with potentially life on them, but you are going to completely revolutionize the rest of astronomy, right? A 10-meter telescope in space, a 12-meter telescope in space. This is a big deal. And it tells us all kinds of things we didn't know before about galaxies, stars, everything you can think of. And what it really does is follow through on this promise by Riccardo Giacconi, who won the Nobel Prize in Physics in 2002 for inventing X-ray astronomy. He was also the first director of the Space Telescope Science Institute. 21st century astronomers are uniquely positioned to study the evolution of the universe in order to relate causally with the chain of causes, the physical conditions during the Big Bang to the development of RNA and DNA, our genetic material. And there really is an actual link between those two things in the way that I'll describe. So the frontier for astronomy is not only to discover these Earth-like planets and prove there's life there, but to figure out how it got there, right? Which is the same way that we got here. And I like to illustrate this profound fact with the answer to a question that Neil Tyson was asked, I think, on a radio show. It's actually a pretty cool YouTube video if you dig it out. What is the most astounding fact you can share with us about the universe? It wasn't his vest. It was the knowledge that the atoms comprise life on Earth. The atoms that make up the human body are traceable to the crucibles that cook light elements into heavy elements, and all the fundamental ingredients of life itself. That's the fusion of hydrogen to helium to carbon to nitrogen to oxygen in the interiors of stars. These ingredients become part of gas clouds that form the next generation of solar systems, stars with orbiting planets, and those planets now have the ingredients for life. So that when I look up at the night sky, and I know that we are part of this universe, we are in this universe, but perhaps more important than that is the fact that the universe is in us. You may have heard we are star stuff, and that is literally true. All the carbon, all the nitrogen, all the oxygen, all the magnesium, iron, everything you can think of here in your bodies in the room came out of a star. That's pretty profound. It's so profound that it has a t-shirt, right? You are here, right? But what we're really saying is not you are here. That's true. We're here. We're in a galaxy. It's more like you were here, right? The stuff in you used to be in a star. It used to be in the interstellar gas. Some of it used to be in intergalactic space because galaxies like to eject material out into intergalactic space over time. So this whole story of the origin of life goes through the intergalactic medium, galaxies, the interstellar medium, supernovae, right? You used to be part of a supernova explosion at some point. This is the whole story of cosmic birth of living Earth. So I want to very briefly go through this evolution from protogalactic seeds through the birth of galaxies, through star clusters, through planet forming into the solar system to tell you how this telescope, this same telescope that's potentially going to discover life on other worlds, is going to blow open this whole story of how that life got there and ourselves. Right? And it's actually pretty amazing to think that even if the life we were to discover were to have 7 heads and to drive on the other side of the road, we would still have this in common, right? We all came out of the same basic cosmic origins, stars, galaxies, and planets. However, whatever language they speak, even if they're just unicellular bacteria, we at least have that to talk about. What we're calling this JWST does an amazing thing. It improves the resolution with which we can observe the universe by more than a factor of 5 in one dimension and 25 in another dimension over Hubble. It allows us to resolve very important thresholds. And I like to illustrate this with a very simple analogy, right? The gain in image sharpness between Hubble, which we've all been marveling about here, right? Go out and look at the Andromeda Galaxy. The image sharpness between Hubble and this JWST is exactly the same as between the standard definition TVs that in the 80s were encased in wooden boxes, right? And the new ultra 4K HD TVs that you can still barely afford, right? It's a factor of 25 in image sharpness. And that's going to totally revolutionize the vision we have of galaxies, stars, and everything else leading up to life. I want to make this very concrete. So we have a great postdoc here who likes to make fake galaxies and compare them to real galaxies and figure out what galaxies are doing. And he's helped me to simulate a galaxy at redshift 2. So this is 10 billion light years away. It's 10 billion years back in time, this galaxy. Hubble has taken pictures of thousands of galaxies that look just like this, right? This looks like real Hubble data. It's a disk galaxy at this early epoch. If we zoom in to its star-forming disk, you really can't see much, right? It's a blur. Even Hubble, which is only 7, 8 feet across, can't make out all the detail. Well, I said JWST is going to fly, and that's true, and it'll do better. Its vision is sharper, but it only observes in the infrared. So it's going to miss a lot of the important light, especially the youngest stars. The blue stars in the Andromeda image out there, those are the youngest stars. They wouldn't really show up in a JWST image that's like this. So it's still, even though it's a sharper picture, it's not capturing the whole range of what there is to see. But this, look at that. Compare that to this, right? Night and day. That's a 12-meter telescope observing in the same wavelength range as Hubble, right? Look at what you can see if you zoom in. Now you're seeing individual star-forming regions, all these little blobs. What used to be just a blur breaks up into individual star-forming regions. You can actually see what's going on there, right? These are the building blocks of galaxies. There's another one. See that little satellite galaxy? Pretty much gone, right? In the images from the other telescopes. So this unique spatial resolution from having this enormous telescope, this 12-meter telescope, allows us to resolve things at 100 parsecs, which is 300 light years, everywhere in the observable universe. Something we've never been able to do before. And that's going to completely revolutionize our ability to understand what galaxies do. Not only that, but actually I just lied to you because I said that was a galaxy. That's true. That's part of a galaxy. But the luminous parts of galaxies, the part you can see, are really only a bit of the story. If I skip ahead, there's a galaxy. But in fact, galaxies are surrounded by this very diffuse gaseous medium, which you can't see in images. It just doesn't light up in starlight. The stars aren't there. But this is the fuel that creates galaxies. And in fact, some of those heavy elements, the carbon, nitrogen, and other stuff that I mentioned earlier, used to be out here in this so-called circumgalactic medium, which found its way into a galaxy, formed stars, planets, people, Toyotas, and everything else. And we've never seen this stuff, right? We know it's there because we can see it absorbing light from the background, but we can't take a picture of it. This observatory will be able to do that. And so we'll be able to see that galaxies are actually surrounded by this rich medium of gas that's feeding them, that's receiving the products of their output. And moreover, this stuff recycles over billions of years. This gas goes in a galaxy, forms a star, gets kicked out again, comes back in this great recycling process. And we can watch that happen if we can fly this observatory. Not only that, if that's not enough, like the knife salesman says, but wait, there's more. At the resolution that this observatory can achieve, virtually every star in the Milky Way moves. Okay, so if you watch a star, you find a star, you wait 10 years, it'll move, right? the velocities we can resolve and detect are actually just kind of mind-boggling, right? Out to the nearest stars, you can detect motion that's as fast as a giant tortoise, right? 0.2 miles per hour. So go to the zoo, watch a giant tortoise. If he walked for 10 years without stopping, and you put him out at 10 parsecs, and then you lit him up, you would be able to see it. So I know that's a lot of ifs, but the point is, it's a really slow motion, right? Virtually every star is moving faster than that. Out to 100 parsecs, out to 10 kiloparsecs, which encompasses the entire disk of the Milky Way, we can detect stuff that's moving as fast as a Formula One racer. Out to the nearest galaxy, like the Andromeda galaxy, anything that's moving about as fast as the space shuttle or spacecraft does in orbit, also detectable motion. And this is amazing because it turns the entire galaxy into a movie, right? You can now study not only the static universe, what stuff looks like when you take its picture, but watch its motion over time. So imagine taking that Andromeda image in the lobby there and seeing it in motion, and seeing all the motions of the stars, and watching all the dynamics of the stars moving and forming over time. It will be possible to do all of this in the future. We'll not only be able to do that, we'll be able to measure the masses of stars, the individual masses of individual stars all the way out past Andromeda. We'll be able to see stars forming in environments where we currently can't. This is a Hubble image of the star-forming region called 30 Doradus. It's in one of our own satellite galaxies called the Magellanic Clouds. And Hubble sees just a blur there. Frank was showing you earlier, a lot of those star clusters in Andromeda are they just become a continuous blur in the center because we don't have the resolution to pick it out. JWST is going to be able to see that, break into individual stars, count them, and work out what their masses are and how they got that mass. Finally, one of my favorite topics is the solar system. We went all the way to the edge of the universe, and now we've come all the way back. But this is just as much a part of origins as anything else. A lot of these outer solar system objects, when we figure out what they're made of, they tell us what some of the oldest components of the solar system are. They tell us how much carbon and nitrogen and oxygen there was in the early solar system when the Earth formed. And they tell us much about the history of our own planetary system that we didn't know before. If you take an image of Pluto with Hubble, it looks like that. Not so great. You can barely make out the fact that it's not a uniform surface. But if you were to do it with this 12-meter telescope, suddenly you can actually see surface features. We can resolve features in the outer solar system at the orbit of Jupiter that are as large as the island of Manhattan, say, right? Which is pretty small, 20 kilometers. One of the coolest things you can do is watch stuff happen on the outer planets. So this is a Hubble observation of the disk of the Galilean satellite. We're now going all the way back to Galileo. He discovered this satellite of Jupiter called Europa. It's the ice world. You've probably seen it in Hubble pictures. Hubble also discovered that it has geysers, right? So those giant ice plates crack open and jets of water vapor come out. This one is probably about 200 kilometers tall. What is that, 120 miles? That's a pretty tall geyser. But we can't actually say exactly how tall it is because Hubble just sees a little bit of an indistinct blur, right? Again, it's a problem of resolution. If you had a bigger telescope, suddenly you can see the structure of those objects, follow their evolution over time, and learn a lot about the outer solar system, even without sending a spacecraft there, which we often do, right? It's great we send spacecraft out there to live in the outer planets for years, but you can't do that for every planet. You can't do it at all times. If we have telescopes here at Earth, we're pretty competitive with the image quality you can get. So there's a lot of amazing stuff you can do with this telescope, apart from finding life, if that's not enough for you. What can it do in particular? Well, you can resolve every galaxy in the universe to 100 parsecs or better. That's 300 light years. You can detect virtually every galaxy that's forming stars at the epoch when our own Milky Way formed, which means you're going to see all the Milky Way's building blocks and the entire history of galaxies like it up through the present. We can observe individual supernovae all the way back to the beginning of the universe. We can see this nearly invisible gas feeding galaxies and receiving their products and recycling. We can watch the motion of virtually any star we choose in the local group of galaxies. And we can see objects the size of Manhattan, the orbit of Jupiter, including those big monoliths. Which is ultimately going to allow us to draw this whole picture of cosmic birth up to life in the present time. So I just want to leave you with the thought that we're building on 400 years of astronomical history, right? Starting with Galileo's first attempt to put a telescope on the sky and figure out what was there, his historical and revolutionary discovery that there was a world out there to know that wasn't terrestrial, all the way through the astronomical pioneers of the last 2 centuries, through our present when we started to grasp the idea that there may be living planets out there, and to think that we're, with 400 years of this history behind us, possibly only 20 years from discovering that life, is a really amazing idea to contemplate. So I'm excited about this. I hope I've got you a little bit excited about this. I'd like you to try to follow our progress as we go along. In particular, the Institute has a site called searchforlife.net where we post a lot of the developments in this field, as well as some more in-depth material about this particular telescope. And there's the usual websites for tracking what the Institute here is doing. I hope that was enjoyable, and at that point I'm happy to take any questions you have.